Okay, onward to our next test to determine whether the endpoints of a power series will converge or not, and just in general a test for an infinite series of constants. I want to show you some pictures here. Okay, so here's an infinite series of constants, 1 over n, and that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. Okay, now just as a quick introduction here, if we try to do the nth term test, okay, which says, okay, take the limit as n goes to infinity of the nth term and see what happens here, we will get 0. And I just want to remind you that that does not mean anything. This series could converge, this series could diverge based on that test. This test is inconclusive. Okay, but we've seen many series that have a nth term approaching 0 that do converge. And I don't know if we've seen any that diverge yet. So we'll talk about that in a second here. Now, one way to look at these numbers, 1, 1/2, 1/3, 1/4, 1/5, is to look at it as the area using a Riemann sum under the curve f of x equals 1 over x. Okay, so let me point this out to you here. The red curve is the curve 1 over x, and I've done a Riemann sum. In this case, it's a left Riemann sum with subintervals of 1 unit, and we've drawn in the rectangles for you. And if you look at these areas are 1, 1/2, 1/3, 1/4, etc. Okay, so it's a left Riemann sum for the area under the curve 1 over x, starting at 1 and going off to infinity. And I think from this picture you could say, well, okay, looks like sigma 1 over n, this series that we started with, and going to 1 to infinity. Okay, if I add up all of those numbers, that's the same as adding up all of these rectangles, areas, and it's very clear from the picture that that series, okay, or those rectangles, is greater than the area under the curve from 1 to infinity, okay, of the function 1 over x dx. And we know how to do this integral. We can tell you whether this integral diverges or converges a couple of sections ago. Okay, so let's just quickly do that. We know that this is an improper integral, so this is going to become a limit. And we'll do the limit as a approaches infinity of integral 1 to a 1 over x dx. That gives us the natural log of a minus the natural log of 1. Okay, I'm skipping a step there that we normally write, the antiderivative. I'm already plugging in the limits, but we need to take the limit as a approaches infinity. Okay, well the natural log of 1 is 0, and the natural log function, when the input goes to infinity, goes to infinity. Okay, so this integral diverges. And if this series is greater than, okay, is greater than that integral, then it must also diverge. Does that make sense? Okay, if this is larger than something that diverges, then this must also diverge. Okay, so we've used kind of a area approach, okay, to look at this series here, and this is going to be the basis for our next test. Before I go on to our next example, though, I do want to point out something, and that's this series right here is very special. Comes up a lot in this unit. We haven't talked about it yet, but this series here, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, has a name. Okay, it's called the harmonic series, and it's kind of a canonical, which means standard or famous, canonical example. Okay, I don't want to say harmonic. Standard example of a series whose nth term goes to 0, but diverges. Okay, so the nth term test says, hey, the limit's 0, inconclusive. I want to think it converges because these terms get smaller and smaller and smaller and smaller. And eventually I'm not adding very much. Okay, but turns out that this series actually diverges. All right, it's going to be a famous example that we refer back to many times because we're going to use it for comparison of other things, and it comes up in its own right. So we need to know the harmonic series diverges and have an understanding why it diverges. I'm going to show you another reason in class on Wednesday, or sorry, on Friday. Okay, now let's take a look at another example here. Okay, I have another series, 1 over n squared, which is 1 plus 1/4 plus 1/9 plus 1/16, etc. And here's the red curve that's similar to that series. This is f of x equals 1 over x squared, which is a continuous function, whereas the series is just the whole number inputs of a function 1 over n squared, okay, being added together. Now, if we take a look at this picture here, I would say that I can look at the integral from 1 to infinity, 1 over x squared dx. That's the area under the curve from 1 to infinity. And I can say that that is greater than this series. Now, I'm missing one of the pieces. I'm missing this piece right here. Okay, if I start at 1, so I'll fix that in a second. But this would be starting at 2 and going to infinity of 1 over n squared. So I would have the 1/4, right? This is the 1/4 right here. I'd have the 1/9, that's right here, etc. And I would say that the integral starting at 1, okay, and going to infinity is greater than that series. And I hope that that's clear, okay, because the series is represented by the areas of these rectangles. Okay, now you're saying, well, what about the 1? Well, okay, let's add 1 to both sides. Add 1 to this side, and if I add 1 to this side, then I can erase that 2, and I can make it the 1 again that I had here. Okay. Now, once again, I have an improper integral. I know how to handle this, and I can figure out whether this converges or diverges. So let's leave that 1 off to the side here, and let's do the same deal. Let's do a limit as a goes to infinity, and let's do an integral from 1 to a of, I'm going to write it as x to the negative 2 this time, and let's see what happens here. Okay, we got 1 plus the limit as a goes to infinity. The antiderivative is going to be negative 1 over x. So I'm going to have negative 1 over a minus negative 1 over 1. So that's a plus 1 over 1. And as a goes to infinity, 1 over a goes to 0. Okay, so here's my 1 plus another 1. So I have 2. 2 is greater than the sigma, the series, 1 over n squared. N starts at 1, goes to infinity. What does that mean about our series? Well, it means it converges. Okay, it's bound above by a value, 2. So 1 over n squared, I can show converges by this argument here. Now, before I go on to the next thing, which is the definition of our test, think about this for a second now. Very similar curves, right? 1 over x squared and 1 over x. Just like we saw with improper integrals, one converged, one of the areas converged, one of the areas diverged. And now we have a similar looking series. This 1 over n squared, very similar to 1 over n, right? Numbers get very small, get close to 0, but this series will converge, the other one diverges. Okay, kind of the mysterious part of this unit. Things that don't make sense, obviously, intuitively, but actually are true. All right, so that brings us to the integral test. And it's a little bit wordy, and you may say, well, do we need all this? And I say, well, maybe, maybe not. Okay, Sarah Romanman is telling me at UT, her professor was very particular about showing all the criteria when you use a certain test. We saw the alternating series last lecture where you guys showed those 3 criteria. So I'm not going to be terribly picky about the integral test, but here's what it says. It says if you have a sequence of positive terms and you compare your sequence with a function, okay, with a function, and your function has to be 3 things. It has to be a continuous function, it has to be always positive, and it has to be decreasing. Okay, so go back real quick and take a look. These functions that we looked at were what? Continuous. Right? If I start at 1 and go to infinity, I'm continuous. Continuous, they're always positive, they're never below the x-axis, and they are decreasing. Okay, and that has to be the case for this argument to work that we're about to mention here. Okay, and it says decreasing for some value of x. So in the beginning, you may get a little bit of increase, but eventually the function has to be decreasing forever, okay, at some point. So there's the verbiage. It's all crazy, but basically your function's got to be three things: continuous, positive, and decreasing. If that's the case, okay, then you're going to compare your series with the improper integral that your series looks like. Okay, so remember, your sequence function in here is compared with a continuous function in here. And we're going to use the argument that if this integral converges, so does your series, just like the 1 over n squared did. Or if this integral diverges, then so does your series, based on what you saw with 1 over n. Okay? Both converge, both diverge. So now you're going to have a nice little tie-in back to improper integrals back in chapter 7 or chapter 8, wherever that was. Okay, so let's do a quick example here. Does this series converge? Does this series diverge? Okay, we can't use the nth term test. It'll be inconclusive. This is not an alternating series. This is not a geometric series. It's not a telescoping series. So that's the next test I have, is the integral test. So what am I going to do? I'm going to compare this with, okay, I'm going to compare this with a continuous function that's decreasing, positive, and continuous, right? So the function would be f of n equals 1 over n to the what? 3 halves? Okay. And then we're going to do the improper integral starting at 1 going to infinity. Okay. So we're going to go, okay, what does this integral do? Does it converge? Does it diverge? That'll tell me what the series does. I'm not going to write f. I'm going to write 1 over x to the 3 halves dx. Okay, so once again, we need a limit. The limit as a approaches infinity of the integral from 1 to a. And let's rewrite this as x to the negative 3 halves this time. Okay, now antiderivative. We're going to add 1 to the exponent, so now we're at negative 1/2. Divide by negative 1/2, also known as multiply by negative 2. We'll evaluate at 1 and a, and then we'll take the limit once that's done. Okay, so I have negative 2. Let's write this over the square root of a. Minus a minus is a plus. Plus 2 over the square root of 1. 2. And we need to take a limit. And this term here heads towards 0. So this comes out to be 2, which means the integral converges, and therefore our series converges. Okay, we don't know what it converges to. That's not the question here. The question is, does it converge, does it diverge? And this converges by the integral test. Okay, did I check the 3 criteria? No. This function, 1 over n to the 3 halves, okay, is a continuous function. The only spot where there's a problem is 0, but we're starting at 1. Is it always positive? Yes. And is it decreasing? Yes, it is. I didn't show it, but if we took a derivative, we could do a sign chart and show that it does decrease. So it does match the criteria for the integral test. All right, your first entrance ticket, 11.3, number 3, that's for both editions. It works. And I'll see you in a second. Okay, you're going to have a lot of series that are of the form 1 over n to the p, with nothing else up here, nothing else in the numerator. And there are some shortcuts here for evaluating these things pretty much in your head. They will expect you and allow you to use this kind of argument here. Okay, so there's certain values of p that are kind of crucial. All right, obviously if p equals 1, then you have this series, sigma 1 over n, which we already saw diverges. Okay, so if p equals 1, that's your series, and you can say, well, I got the harmonic series, which I know diverges. Okay, so that's kind of the buffer point here. Now, if p is bigger than 1, okay, if p is bigger than 1, then your series will converge. Okay, now think about why that is. Okay, if you have an integral of 1 over n to the p, where p is bigger than 1. Okay, so we did n squared already. Remember, we're comparing this with a real valued function that's continuous. So let's do 1 over x squared. Okay, you could also do this for 3/2, like you just did, or 4/3, etc. When you do the integral, what happens? You do an antiderivative, right? And you add 1 to the exponent. Well, right now this is x to the negative 2, and if you add 1 to -2, you'll have -1, which means this is still in the denominator. Okay, this x will be 1 over x, and that's going to be true for any value of p bigger than 1. You will still have a term in the denominator which gets canceled out to be 0 when you plug in the infinity. That's why this works. Okay, vice versa, if p is less than 1, okay, if p is less than 1, then your series is going to diverge. Okay, let's take a look at y real quick here. Let's say you had 1 over x to the 1/2. Okay, 1/2 is less than 1. Well, you're going to add 1 to the exponent, which makes it x to the 1/2 go into the numerator, and then the 2 goes in front. That's your antiderivative, and if you're plugging in infinity into this, that goes to infinity. Okay, so your integral is going to diverge, therefore your series diverges also. Okay, so they call the series that look like 1 over n to the p a p-series. Okay, and so what happens is if you have a p-series, you can just look at it and say, oh, p is less than 1. Okay, this is a p-series with p less than 1, therefore diverges. Or, hey, p is 6. P is 6, that's greater than 1. So it's a p-series with p more than 1, it converges. And they will allow you and expect you to be able to do that pretty quickly here. Okay, so you can do this problem real fast. Just write out the necessary verbiage, and you'll be done real quick. 11.3, number 9. All right, obviously, not all the ones we do with the integral test will be p-series. There'll be ones that you actually do have to do the integration. And how will you know to use the integral test? Well, you're going to look at your series, go through the other tests that you know, and if you can't do those, you might look at that and say, could I integrate the function that's associated with that sequence? And if so, the integral test may be what you want to go after. Send me some questions, at least one, and we'll see you in class on Friday. Bye-bye.